Hello. In this video, I'm going to explain problem 17 from the 2013 F=ma contest. In this problem, we have two small equal masses attached by a lightweight rod, and the object orbits a planet, and we are asked two questions about the nature of this setup. One is there a force in the rod, and what kind of force is it, tension or compression, if it's there at all? And second, we're asked about the stability of this equilibrium. So, fundamentally, this is a question about tidal forces. And so what are tidal forces? Tidal forces occur really in any macroscopic object due to differences in the strength of gravity from point to point, from place to place. So the classic example of this is the Earth and the Moon. So here we have the Earth, and here we have the Moon. Obviously not to scale, especially in terms of the distance between the Earth and the Moon. But basically, what happens is that the water that is closer to the Moon on the side facing the Moon is slightly closer to the Moon, and so it gets attracted to the Moon slightly more strongly than the Earth itself. And the parts of the water that are farther away from the Moon get attracted to the Moon less strongly than the rest of the Earth gets attracted to the Moon. And as a result, the water will bulge out on both sides. And this is where we get the tides from. And in fact, tidal forces are actually named after these tides, the tides of water on the Earth. And so this is sort of the most famous example and the one that is named after. And so now, what does this mean in general? So suppose we have, some object attracting gravitationally, and we have some macroscopic object like this. Well, what happens is that the force on the side closer is stronger than the force on the side that is farther away. Also, if you look at something off to the side, then there's a slight angle. So it won't be pulled in exactly the same direction, but rather it'll be pulled at a slight angle. So it'll look like this. And this side will get pulled like this. And so what do we see? Well, what we see is that since the closer side gets attracted more strongly, and the farther side gets attracted less strongly, we actually have stretching in the parallel direction. And when I say parallel direction, I mean the direction of the line that connects the two objects. And then we actually have squeezing in the perpendicular direction. And so any direction that is perpendicular to the line joining the two objects, the object will be squeezed slightly. And you can see that because this side is attracted slightly more this way, and the left side and the right side is attracted slightly more to the left. And so the extreme example of this, another famous example of tidal forces, is a black hole. And what happens when you get too close to a black hole is that you will get stretched out extremely in a very extreme fashion, and you will also become very thin in an extreme fashion because you get squeezed in the perpendicular direction, and you get stretched out in the parallel direction. And so these are so extreme that it gets called spaghettification. I cannot spell spaghetti. spaghettification in the extreme case. And so that is a visualization you should keep in mind. That yes, this is the extreme case, but on a less extreme example, this is what happens in general. And so now we can look back to our example of a rod orbiting the Earth, or orbiting some planet. So what happens is that there is stretching in this direction. And so what happens is that this means that there is a tension force in the rod. So basically, tension force basically means that the net force is basically attempting to stretch the rod and make it longer. And compression means that the net force is attempting to squeeze the rod. And so now, what about the stability of this equilibrium? Well, again, let's suppose hypothetically that this rod gets deflected by some slight angle like this. Well, as we discussed, there is a squeezing in this direction. So it looks like that. That this particle will want to move slightly this way, and this particle will want to move slightly this way. And so actually, we can see that this actually restores. Of course, the total forces on these objects don't actually point in that direction. The total forces point inward. But the differences between these two forces act in roughly these directions. And so what we get is that these particles will actually want to move back into equilibrium. And because you can see that this is the tidal forces are restoring. And thus this is a stable equilibrium. And so tension is what we want. And so we go back, and we see that the rod is in tension, and the equilibrium is stable. Another way to see this result a little bit more clearly is to basically go into the co-rotating frame. As basically that is the frame of the rod itself. And so here is the rod. We can draw it larger now. And so in this frame, the rod is stationary. And now this will allow us to only look at the differences in force. And so let's say, for example, if the frame is centered on the center of the rod, then compared to the center of the rod, this particle will be pulled slightly toward the planet, and this particle will be pulled slightly away because here gravity is slightly weaker. And here gravity is slightly stronger. And thus we indeed see that the rod is in tension. And also, if the rod gets deflected by some angle, then what will happen is that the net force will point somewhat toward, but then also at an angle, and this force will point slightly away and then also at an angle, like this, pointing back toward the line connecting the two objects. And so once again, we see that this is a restoring force, or a restoring torque, so that the equilibrium is stable. And so that concludes this problem. Thank you for watching, and I hope that was helpful.